we have done in the lecture so far is that established through experiments, and that is very important to understand experiments, that number 1, black body radiation, and that means its spectral density can be explained by taking the energy levels of an oscillator quantized. And what does that mean? That means if an oscillator has frequency nu, it can take energies 0, h nu, 2 h nu, and so on, in, that is, in quanta of h nu. And through this we obtained a spectral density curve that fitted the experiments perfectly. And it also went to, in the two limits, nu over t being very large and very small, it went to the respective Wien's and Rayleigh-Jeans formula. Number 2, not only this, what we also saw is that radiation itself can be thought of as composed of, let us call, radiation molecules, and I am using that term deliberately to show you, because it came from the considerations of entropy change of radiation when it expanded, keeping the energies the same, and the volume increased from V 1 to V 2, and it was the same as an ideal gas. So, radiation molecule and then called photons that have energy h nu for radiation of frequency nu. So, on one hand I have oscillators that radiate, that have energy h nu, 2 h nu, and so on. On the other, radiation itself has energy h nu. Now, the question that arises, and let me write that question, is quantization. That means energy coming in units of h nu, 2 h nu, and so on, limited to oscillators that radiate, and radiation. Now, let me explain that. Oscillators that radiate are charged particles. As they accelerate and go back and forth, they start giving out radiation of the same frequency, and radiation of course is light or whatever. So, is it limited to this, or is it more general, or, so let us pose that question, or is quantization a law of nature? And that means, does it apply to other systems like mechanical oscillators, and we will see atoms and all that. And it turns out that this is more general. and it becomes a law of nature. So, all this built up slowly. So, now in this lecture what we are going to discuss is that the quantization rule applies to mechanical oscillators also. One thing you must keep in mind through all this is that test of any theory or hypothesis is its confirmation by experiments. That is what science says. Whatever I can propose should be verifiable by experiments, or must explain an experiment and experiments based on the experiments, or experiments to do that, check that theory. So, the background. Background, I am going to give you a specific heat of insulators, and what was known in this was something called the Dulong-Petit law. That said that specific heat of insulators is 3 R per mole, and this was based on equipartition theorem. Recall what equipartition theorem is. Equipartition theorem says that energy per degree of freedom is kT by 2 for a molecule. So, per mole the energy is going to be n Avogadro times k T by 2, which is nothing but R T by 2. What Dulong and Petit observed is that for atoms in a solid, the energy is 1/2 mv square average kinetic energy and 1/2 kx square average potential energy. Both are quadratic and both average RT by 2 RT by 2 for each degree of freedom. Now, this is in one dimensional case. In 3D, what we are going to have, so if there is a 3D solid, by 3D I mean 3 dimensional, each atom has 3 degrees of freedom. So, each atom has energies, kinetic energy is 3 by 2 mv square, which average value, by this bracket I mean average, is 3 R T by 2 per mole, and potential energy is 3 by 2 k x square average is going to be 3 R T by 2 per mole. So, the total energy is going to be 3 R T, and therefore, the specific heat, that means specific heat per mole, is going to be 3 R T d by dt equals 3 R, which is roughly 24 joules per mole. R is roughly 8 joules. Now, this was fine. This is what was observed, that if you plot specific heat versus T, it was roughly 24 joules. However, as T went down, as T was reduced, what one observed was that the specific heat went down and became 0, like this, for T tending to 0, and this could not be explained. This could not be explained by classical equipartition theorem. Could quantum theory come to rescue? And that is precisely what happens. Now, we have already seen earlier while discussing the development of quantum theory that equipartition theorem did not hold in case of black body radiation. If it did, Rayleigh-Jean's formula would have been all right. So, one should not expect that it would hold in other systems if this is a general theory. So, let us see now how quantum mechanical ideas at that time explained the specific heat going to 0 as T goes to 0. Now, we have already calculated that average energy per oscillator is equal to h nu equals divided by E h nu by k T minus 1. This is what we had calculated. Just to recap, how did we do that? We said that an oscillator can have energies 0, h nu, 2 h nu and so on, and probability of having energy n h nu is nothing but e raised to minus n h nu by k T divided by summation over n equals 0 to infinity e raised to minus n h nu by k T. And we multiplied by the probability with the energy and we got the average energy E average at temperature T was equal to n h nu e raised to minus n h nu over k T summed over n equals 0 to infinity divided by summation n equals 0 to infinity e raised to minus n h nu over k T, and this gave me h nu over e raised to h nu over k T minus 1. And therefore, for n particles, I am going to have three n, that is 3n degrees of freedom, and each degree of freedom has energy e raised to h nu over e raised to h nu over k T minus 1. This is going to be the energy of the system E T. So, for a solid that has n atoms, each degree of freedom has frequency nu, the total energy E T is given by 3 n h nu over e raised to h nu divided by k T minus 1. So, we found applying quantum ideas, energy for n particles is going to be 3 n h nu over e raised to h nu over k T minus 1, and therefore, specific heat. I am not going to the subtleties of whether it is constant volume or constant pressure. For solids, it does not really matter if their compressibility is very small. So, Cp and Cv do not really differ by much. It is going to be dE by dt, which is going to be 3 nh nu d by dt of 1 over e raised to h nu over k T minus 1, which is nothing but 3 nh nu divided by e raised to h nu over k T minus 1 square times e raised to h nu over k T times h nu over k T square. So, this is equal to 3 n h square nu square over k T square e raised to h nu over k T over e raised to h nu over k T minus 1 whole square. And if you plot it as a function of temperature, as T goes down, this fellow goes to 0 exponentially. To see this, let T go to 0, then e raised to h nu over k T goes to a very large number, and therefore, I can write C as 3 h square nu square over k t square e raised to minus h nu over k t, and that goes to 0. So, that explained that specific heat should go to 0 as T goes to 0 if we follow quantum ideas, and that again established the trust in quantum theory. Let us see if it leads to Dulong-Pettit law also. So, what we have calculated is C equals 3 h square nu square over k t square e raised to h nu over k t divided by e raised to h nu over k t minus 1 whole square. Now, as t goes to a large value, I can write e raised to h nu over k t roughly equal to 1 plus h nu over k t, and therefore, C is 3 h square nu square over k t square times 1 times 1 over 1 plus h nu over k t minus 1 whole square, and that becomes 3 h square nu square over k t square times 1 times k square t square over h square nu square. And if we cancel terms, h square nu square goes, one of the k's goes with one of the k's here, and t square also cancels, and you get the result, which is 3 k times n, or 3 k per atom, which is indeed 3 r. So, not only when I apply quantum ideas to mechanical oscillators, I explain that C goes to 0 as T goes to 0, it also goes to the correct limit in high temperature. By the way, this model of calculating C is known as Einstein model. So, I conclude this section by emphasizing that Einstein applied the ideas of an oscillator having quantized values of energies to explain the vanishing of specific heat of solids as temperature goes to 0, and that gave a little more trust in quantum theory. In the coming 2 lectures this week, I am going to now discuss how quantum ideas were also applied to other systems to explain say hydrogen spectrum and the energy levels of an oscillator in general, and this sort of started building up quantum theory.